Hello students, welcome to physics class. Today we discuss Ampere Circuited Law and its application. You know that Ampere Circuited Law is an alternative form of Biot-Savart law in magnetostatics. You know that by Biot-Savart law we can find magnetic field due to any current carrying conductor. And according to Biot-Savart law, the magnetic field produced by a current carrying element dl is given by dB is equal to mu 0 by 4 pi I dl sin theta by r square. But practically, it's very difficult to apply this Biot-Savart law other than a straight line conductor or circular coil. So now let us see another alternative form of Biot-Savart law, which is known as Ampere Circuited Law. Let us see what is the statement of Ampere Circuited Law. The Ampere Circuited Law states that the line integral of magnetic field B around any closed circuit is equal to mu 0 times the total current I threading or passing through the closed circuit. That is, according to Ampere Circuited Law, or Ampere Circuited Law states that the line integral of the magnetic field B around any closed circuit is equal to mu 0 times the total current I threading or passing through the closed circuit. And mathematically we can write as the line integral, actually this shows that through a closed path. The line integral B dot dl is equal to mu 0 times I. Mu 0 is the permeability of vacuum or free space. Mu 0 times I. Okay. Now, let us how to apply this Ampere Circuited Law for a straight line conductor. A current carrying straight line conductor will produce a magnetic field. First, let us see what is the nature of magnetic field produced by a straight line conductor. Here we have a straight line conductor. Here a straight line conductor having infinite length. Say I current is passing through the straight line conductor. We know that around the straight line conductor there is a magnetic field. When any other magnetic material or substance comes, magnetic substance comes around this conductor, it will experience a magnetic force. So we can say there is magnetic field around that conductor. And so what is the nature of the magnetic field? The nature of the magnetic field is, or the magnetic field direction can be determined by drawing the magnetic field lines around it. It shows that the magnetic field around this straight line conductor is somewhat concentric circle. The magnetic field lines, the shape of the magnetic field lines around the straight line conductor will be some concentric circle. Already in the 10th standard, we drawn the magnetic field lines due to a straight line conductor. We know that they are the concentric circle. So some magnetic field lines shown around this conductor. And what is the direction of magnetic field can be predicted by right hand thumb rule. How to apply the right hand thumb rule for a straight line conductor? For example, if it is a straight line conductor, to suppose the current is passing through this conductor in the upward direction, this is the direction of current. So to apply this right hand thumb rule, so suppose you are holding this conductor with your right hand in such a way that thumb point in the direction of the current. In this case, current, suppose the current is in the upward direction. And so if you are holding the right hand in such a way that, okay, we are holding this conductor in such a way that the thumb point in the direction of current. And the curved fingers show the direction of magnetic field. That's why the direction is shown here. That is the magnetic field lines and the direction of magnetic field due to a straight line conductor. The magnetic field lines are concentric circle around this straight line conductor. And throughout this region, we have a magnetic field. Now, let us find what is the magnetic field or the magnitude of magnetic field at a particular point. We want to find the magnetic field, this a straight line conductor. We want to find the magnetic field at a point P, which is at a distance r from the conductor. So a point P is situated at a distance r from the conductor. This is the direction of current. We are going to use this Ampere Circuited Law. To apply this Ampere Circuited Law, we are imagining a circular Amperian loop. To apply the Ampere Circuited Law, we are using an Amperian loop. Okay, remember, to apply this Gauss's theorem in electrostatics, we constructed a Gaussian surface, an imaginary closed surface. So in order to apply this Ampere Circuited Law, we have to imagine a closed path of current, a closed path. We will call it as Amperian circuit or Amperian loop. So consider such a circular Amperian loop of radius r. We can divide this Amperian loop into very small element dl, infinite number of small element dl like that. At every point we have magnetic field, because around this conductor we have magnetic field. What is the direction of magnetic field? At this point, okay, this is a very small element dl. At this point P, the direction of magnetic field can be predicted by using a right hand thumb rule. Apply right hand thumb rule here. At this point, you can see if you are grasping the conductor like this, at this region, the magnetic field is going perpendicular to the plane of this board and inward. Okay, perpendicular to the plane of board and inward. At this point, suppose the point is here, we are holding the conductor like this. Actually, all these fingers, curved fingers are coming out of this plane. So the magnetic field is perpendicular to the plane of board and outward. In all other region, we can show that the magnetic field is along the tangent of this circle or tangent to this Amperian loop. So angle between B and DL at any point of this loop will be 0. So at this point, first we are finding the B dot DL at this point, the line integral of B and DL at this point. That is B dot DL is equal to B DL cos 0. At this point, the angle between B and DL is equal to 0. Throughout this circle or throughout this Amperian loop, the angle between B and DL is equal to 0. So we can just integrate from throughout this length. That's why B into integral DL. What's integral DL? The circumference of this Amperian loop. That's equal to 2 pi r. That's equal to B into 2 pi r. First to find the B dot DL for a single point, and throughout this loop the total is integral B dot DL. That's equal to integral B into DL. That's equal to B into 2 pi r. Integral DL, it means the length of this Amperian loop. The length of the Amperian loop is equal to 2 pi r, circumference of the circle. Now, from Ampere Circuited Law, we know that line integral B dot DL is equal to mu 0 times I, where mu 0 is the permeability of free space. Our conductor is placed in vacuum or free space. That's why we can use mu 0. If it is not in vacuum, the permeability of that medium should be used. So mu 0 times I, and B is equal to mu 0 I by 2 pi r. B is equal to mu 0 I by 2 pi r. That's the magnetic field at a point P, which is at a distance r from the conductor. We can see that when the distance from the conductor is increases, the magnetic field is decreases. Very close to the conductor, the magnetic field is maximum. With increase of distance from the conductor, magnetic field is decreases. B is inversely proportional to distance. B is inversely proportional to distance. If you are drawing a graph between distance from the conductor and the magnetic field, it will be like this, inversely proportional. With the increase of distance, the magnetic field is decreases. And very close to the conductor, magnetic field is maximum. When the distance from the conductor increases, the magnetic field decreases. By drawing the magnetic field lines also, we can show that. You can see that here we can draw the magnetic field lines very close to each other. Very near to the conductor, the magnetic field lines are very close to each other. When you are moving away from the conductor, the separation between the magnetic field lines also increases. Now let us see how can we use Ampere Circuited Law to find the magnetic field produced by a long solenoid. You know that a solenoid is an insulated copper wire wound closely in the form of a helix. A solenoid is an insulated copper wire wound closely in the form of a helix. So when current is passing through a solenoid, you know that every current carrying conductor produce a magnetic field. Solenoid is also produce a magnetic field. Let us see what is the nature of magnetic field produced by the solenoid, and then what is the intensity of magnetic field produced by a solenoid. We can derive an equation for magnetic field produced by a solenoid by using Ampere Circuited Law. For that, here a sectional view of a long solenoid is shown here. And in this diagram, these are the turns of this solenoid and a sectional view is shown. A enlarged sectional view. In this diagram, this dot mark shows that the current coming out of this plane of this board. Here we can see some dot mark. Here some dot mark is shown. That actually shows that the current is coming out of the plane of this board. And some cross mark is shown at the lower end of this wire. And actually it shows that the current is entering to this plane of this board. When you are taking a single turn of such a solenoid, here we are taking a single turn of such a solenoid, and the magnetic field produced by this solenoid is very close to the solenoid is concentric circle, just similar to our magnetic field produced by a straight line conductor, concentric circle. And when we are moving away from the conductor, the radius of that circle increases, that is the magnetic field lines become larger and larger. So you can see that concentric circles are shown here for the first turn, this for the second turns and third turns, like that. See the direction of this magnetic field. Actually this is the interior portion of the solenoid, and this magnetic field are getting added along the axis of this conductor or axis of the solenoid, because the direction of the magnetic field produced by each and every turn is same along the axis of this solenoid. But you see, along the perpendicular direction of this axis, here the magnetic field produced by this turn, actually this is in this direction, and the magnetic field produced by this turn is just opposite of that one. So they are getting cancelled. That is, the magnetic field produced by this turn is in this direction. The magnetic field produced by this turn just opposite of that. So what happened is that the magnetic field perpendicular to the axis inside the solenoid are getting cancelled. But see, the magnetic field along the axis is getting added, because all the turns produce magnetic field along the axis in same directions. Okay, that is the magnetic field in the interior of the solenoid. We have a magnetic field along the axis of the solenoid. There is no magnetic field perpendicular to the axis of the solenoid inside the solenoid. Well, consider a point outside the solenoid. Suppose we have a point Q just outside the solenoid. For that solenoid, okay, a point outside the solenoid, the magnetic field produced by this dot mark points are just cancelled by the magnetic field produced by the cross marked point. So, outside the solenoid at the point Q and P, the magnetic field are negligible or tends to 0. And inside the magnetic field, you can see that the magnetic field produced by each and every turn along the axis are getting added, and almost they form a uniform magnetic field. That's why inside this solenoid or very near to the axis of the solenoid, almost magnetic field lines are straight line. It shows that we have a uniform magnetic field inside the solenoid. That's the nature of the magnetic field produced by a solenoid. Inside a solenoid, there is a uniform magnetic field along the axis of the solenoid, and there is no vertical component along the axis, and outside the solenoid the magnetic field are very less or tends to 0. So another sectional view of the solenoid. This is actually a very enlarged view, And another normal sectional view of magnetic field for a solenoid is shown. Actually, this is a section, a longitudinal section of a solenoid. These are the ends of the solenoid. Once you are cutting a long solenoid like this along the axis, it will be look like this. And this is the interior portion of the solenoid. And the magnetic field is shown by using parallel magnetic field lines. And this is the end of the turns. Actually, once you are cutting, these are the end of the solenoid. And once the dot mark shows that the current is coming out of the plane of this board, and this cross mark shows that the current entering to this plane of this board. So we have a uniform magnetic field inside the solenoid along the axis of the solenoid. That is shown by parallel magnetic field lines. Now we want to find what is the magnetic field inside the solenoid. For that, we are using Ampere Circuited Law to find the expression for the magnetic field due to this long solenoid. Actually, we are using the concept of a long solenoid. A long solenoid means the length of the solenoid is very large. And compared to the length of the solenoid, the area cross section is very less. We are using such an assumption to derive this equation. Then only the equation for the magnetic field is valid. So that here first we are constructing an Amperian loop, a rectangular Amperian loop A, B, C, D to apply Ampere Circuited Law. You can see this Amperian loop. Half of the Amperian loop is actually well inside the solenoid and half outside the solenoid. Now we want to apply the Ampere Circuited Law through this rectangle or through this Amperian loop. So first, okay, we can write by Ampere Circuited Law the line integral of magnetic field B dot dl is equal to mu 0 times the total current through the loop ABCD. Okay, our loop is actually ABCD. Okay, once you have closed loop A, B, C, D, A. A closed loop of A, B, C, D, A. Okay, now what is mu 0? The permeability. Permeability of vacuum. Suppose this is an air core solenoid or the inside the solenoid we have vacuum. So we can use the permeability of vacuum, that is mu 0 into total current through the loop A, B, C, D, a closed loop. Now B dot dl, the line integral B dot dl is equal to, first find B dot dl from A to B, that is A to B B dot dl plus B to C B dot dl plus C to D B dot dl plus D to A B dot dl. Now we complete a closed path. That is, first find the line integral of magnetic field from A to B B dot dl plus B to C B dot dl plus C to D B dot dl plus D to A B dot dl. Okay, throughout this rectangle we are finding B dot dl. But you see the line integral B dot dl from B to C is equal to what is from B to C. If you are finding the B dot dl, first to see what is the angle between B and dl. We are taking a length element like this, a very small length element dl here. And you know that the direction of magnetic field is perpendicular that. The magnetic field and our length element are perpendicular to each other. The angle between B and dl from B to C is 90 degree. That's why from B to C, B dl cos 90. We know that B dot dl is equal to B dl cos theta. Here theta is equal to 90 degree. That is B to C, B dl cos 90. That's equal to 0 because cos 90 equal to 0. So B dot dl from B to C is equal to 0. And what about C to D? We have an assumption. The magnetic field outside the solenoid is very weak or tends to 0. So B equal to 0. From C to D, B dot dl is equal to 0 because B equal to 0. Outside the solenoid at this point, B is equal to 0. In this region, B is equal to 0. That's why this term is also 0. C to D, B dot dl is equal to 0. And now D to A. What is B dot dl from D to A? D to A. B into dl into angle between B and dl. B is in this direction. dl just perpendicular to it. The angle between dl and B is equal to 90 degree from D to A. That's why B dl cos 90, that's equal to 0. Okay. Now we have only one term, that is the line integral B dot dl is simply equal to A to B B dot dl. A to B B dot dl. Okay. So from A to B, what is angle between dl and B? Here this is the direction of dl and this is the direction of B. B and dl are parallel to each other. The angle between B and dl from A to B is equal to 0. So we can write as, okay, from A to B, B dot dl is equal to line integral A to B, B dl cos 0. Angle between B and dl is equal to 0. Okay, now B into cos 0 is 1. So we take B outside because we have a uniform magnetic field inside the solenoid. B into integral dl. This integral dl actually we have a uniform magnetic field throughout the length of the solenoid, and suppose from A to B the length of this Amperian loop is L, so we can write this B into L. The length of the side AB, that length of this Amperian loop is L, so we'll write as B into L. Integral dl is equal to B into L. Okay, now let n is the number of turns per unit length. You know that it's a long solenoid. There will be many numbers. Okay, we can produce infinite number, or we can produce a many number of turns for a solenoid. So better, instead of saying the total number of turns, we can use the number of turns per unit length. The number of turns per unit length. It means total number divided by length of the solenoid. That's the turns per unit length. So let n the number of turns per unit length of the solenoid. So for the total number of turns, we can write as n into n, because number of turns per unit length, n is equal to total number by l. So total number is equal to n into l. That's why total number of turns is equal to n into l. So what is the total current threads through this loop? What is the total current inside this Ampere loop? How many times the current enter the loop? So that can be write as, inside this loop how many turns are there? Inside this Ampere loop how many turns are there? N into L, because L is the length of our Ampere loop. So N into L gives the total number of turns inside this loop. So how many times current enter to the loop? Ni into L. Ni into L times the current enter or threads the loop. So we can write as mu0 NIL. That is mu0 into total current. This is actually the total current. Mu0 into our total current NIL. Now apply into our Ampere Circuited Law. Now that B dot dl is equal to B into L. So B into L is equal to mu0 into I. B into L is equal to mu0 into I. What is I? NIL. So BL is equal to mu0 NIL, or B is equal to mu0 NI. The magnetic field B is equal to mu0 NI. That is the magnetic field inside a long solenoid. Inside a long solenoid, we have a uniform magnetic field. B is equal to mu0 into N into I. What is mu0? The permeability of vacuum or permeability of free space. If it is air or vacuum inside the solenoid, we can write as mu0 into N into I. If you are inserting any other magnetic material having a relative permeability mu r, we can write that, suppose we have a solenoid like this way, this is a solenoid, and suppose inside the solenoid we are inserting any magnetic material of permeability, relative permeability mu r, we will write this magnetic field is equal to B is equal to mu0 into mu r into Ni. That will be the magnetic field. This equation can be used only for air cooled solenoid. or inside the solenoid if it is vacuum. If it is not vacuum, if we are inserting any material having a relative permeability mu r, we will write the equation for magnetic field as B is equal to mu 0 into mu r into n into y. That is the magnetic field. But when you are deriving, we use many assumptions. That's why the magnetic field is not uniform actually inside the solenoid. Very near to the end of the solenoid, there is some changes in magnetic field. And it is observed that very near to the end of a long solenoid, this equation is not valid. And at the end of this conductor, near to the end of the solenoid, the magnetic field is actually the half of the field inside or at the center of the solenoid. If B is the magnetic field near to the center of the solenoid, and it is observed that, or we can prove that the magnetic field near to the end of the solenoid is equal to B by 2. So here we have a graph which shows the variation of magnetic field with the length of the solenoid. Here, this is the center of the solenoid, actually origin or center of the solenoid, and on this axis we have taken the magnetic field. Okay, the length of the solenoid is taken on both sides, distance from the center. When at the center, almost we have a uniform magnetic field. In some region we have a uniform magnetic field. But when the distance from the center is increases on both sides, we can see that there is a decrease of magnetic field. And when it reaches at the end of the solenoid, this is the point at the end of the solenoid on both sides, you can see that magnetic field is somewhat B by 2. The magnetic field near to the end of the solenoid is equal to half of the magnetic field well inside the center of the solenoid. And however, we can say that there is almost a uniform magnetic field near to the center of the solenoid, well inside the solenoid. And it having a magnetic field of mu 0 Ni for an air cooled solenoid, or if it is vacuum inside. If it is not vacuum, if you are inserting any material root having a relative permeability mu r, the magnetic field is equal to B equal to mu 0 into mu r into n into I. And at the end or near to the end of the solenoid, the magnetic field is almost half of the magnetic field near to the center of the solenoid. That's all today. Thank you.